Okay, so we will continue with the next talk. The speakers are Florian Grunow and Felix Wilhelm, two guys of ERNW. And because in our company we like to break things, and they like to break a cluster file system from IBM, which is quite funny. And yesterday in the evening I was talking to these both guys because they are working on their laptop, and it was like, oh, we have to finish our slides. Yeah, for the talk tomorrow. Yeah, and Flo was so honest to tell me the last changes he did was about 10 minutes ago. So that's kind of new internal record for ERNW. So let us see if it helps some well.
Thanks. Yes, so hi everybody, Florian, Felix. We're going to talk about IBM's GPFS. We called this talk General Pr0ken File System. The alternative was General Portable File System, but we thought that, and you will see this in a minute, there were so many structural and architectural problems in GPFS that we thought that General Pr0ken File System is the better approach for now. So this is what we're going to talk about. We're going to give you a technology overview over what GPFS is, what it does, how it is set up. We are going to dig into the guts of GPFS because we had to. It turned out that we had found a vulnerability that at first glance looked like it was easily exploitable, and yeah, so we are going into detail with that. It wasn't that easy to exploit, I can tell you that for now. Then we're going to take a look at the remote view, an attacker's remote view of GPFS, and after that we are getting to the core. I'm not going to say any details about that now, and afterwards we will have a Q&A session where you can ask questions. Okay, so let's start. So IBM's General Parallel File System is the real name, and it's a cluster file system. And if you Google it a little bit, the features include that it's fast, simple, and is scalable. So basically you can think about it of multiple nodes that get interconnected and they share their data over the network. And there are two main operating modes. One is the nodes are connected to a SAN, and the other one is that there's some kind of network shared disk, which means that there are disks attached to the nodes and they get shared among the hosts. So you can access the data from one or the other node. Different operating systems are supported by GPFS. We are going to look at the Linux version and the version GPFS 3.5. GPFS has a really long history. If you look at the binaries, some of the binaries, they all start with TS or MMFS. TS stands for Tiger Shark, which actually already sounds quite aggressive and problematic, maybe. Tiger Shark, and Tiger Shark is a file system that came out in 1993. So we are talking about a technology that is quite old. So under the hood, many of the components that are under the hood are really, really old. Who uses it? Many supercomputers use it as their file system, their clustered file system, and in cluster architecture, it is quite widely used. So looking at the components that you have when you need to run a GPFS system, a GPFS cluster system, you will have three main components, to say so. You have user space utilities. There are a lot of binaries laying around on the file system. There are shell scripts, big shell scripts. Some of the binaries are just linked to each other, and depending on which name they have, they execute different code paths, and there are some setuid binaries too, which is quite interesting for us. Then we have a communication daemon. The communication daemon is running on all of the hosts that need to communicate in the cluster, and they use a proprietary communication protocol which is used via TCP. Then we have a kernel module. This kernel module is only supplied binary only, and they have written a wrapper module where the source code is available. We don't know why this is. Maybe this is some GPL stuff. We have no idea. So we need you to remember this structure, this threefold structure. So we have user space utilities, we have a communication daemon, and we have the kernel module. Okay, so let's start with the user space binaries. So digging into the guts of GPFS was possible for us because we encountered it during a penetration test. And what you do during a penetration test when you need to get local root on a system, you need to elevate your privileges. One of the first things that you do is look at setuid binaries that are on the system and that you don't know. Because maybe there is an attack surface and maybe you can actually elevate your privileges depending on how the utilities work. So in this case, this is an incomplete LS over the more of 200 binaries that come with GPFS, and all the ones that are marked in red are quite interesting because these are the setuid binaries that we have been looking into, or some of them. So one binary came to our attention and it is called TS status, and this basically prints some status information about the file system. So if you have this binary, if it's setuid, as a penetration tester, what do you do first? Yeah, I'm sorry, you're involved. So this is a talk, but yeah. What do you do? So you feed it some garbage, right? Okay, so feed it a bunch of A's or something to see if there's a buffer overflow and if the application crashes or something. That wasn't feasible. We fed it some like 1,000 A's, and then there was an error message which stated, hey, the cluster file name can only be more or can only be less than 512 bytes. So out of the box, no buffer overflow there. What else can you do? Especially when you look at this. So TS status, user-supplied input is coming out there. Format string, oh, very good. Yeah, so we tried that, and if you look at it, perfect. This seems to be a format string vulnerability because we're feeding it a %x, and what %x does is if you're not using printf, the printf family in a correct way, it basically prints one value of the stack. So here we go, we have now a value of the stack, so it's not showing %x anymore, and it's showing something like an address or something, and this really looks like a simple, plain old format string vulnerability. So by playing around with it, we definitely found it is vulnerable to a format string, so we could dump values from the stack. When we're using %n, we could do a segmentation fault on the binary because with %n, attacking a format string vulnerability, you basically write a value to an arbitrary memory address, and in this case, that led to a segmentation fault in the binary TS status. And then we encountered something that made us worry for like 1 or 2 minutes, but we didn't think about it. When we used %s, we got this message: lost connection to the file system daemon. So the MMFS daemon, the GPFS daemon, crashed, and the complete file system went away. So we were thinking about this. We couldn't come up with an idea why this is, but we thought, well, let's move on. We submitted the vulnerability and the proof of concept to IBM. We thought it's clearly exploitable. This should not be a hassle. It's a standard format string vulnerability. Should be pretty straightforward. We were thinking all the time, okay, but why did the file system daemon crash? And we couldn't come up with an idea. After a few weeks, IBM acknowledged us and sent out this CVE, and they stated because our POC obviously was not a remote code execution or a local code execution. They stated that this is basically just a security vulnerability that results in a denial of service condition. And it has not yet, which is interesting because, yeah, at this point, it was really not yet shown to cause any other effects besides the program terminating. And if you're a security researcher and you read such kind of an advisory and you read the words setuid command, then you think, yes, challenge accepted. It's not proven to be exploitable right now. There is only denial of service condition. And so we called NO and told, maybe we have a nice talk for troopers. And we called him up and said, like, maybe we should put this on the agenda. This might be interesting, and so we started investigating the exploit. So it was research time for us. We were just using our standard tools, GDB running. We're looking at how the binary was behaving when sending %n, when dumping the stack. it pretty much straightforward looked like, still looked like a format string vulnerability, as you can see here, and we still had no clue why the file system actually is crashing when you're using %s. So what we did to get a little bit more of understanding on how the binary works, we used strace and just took a look at it, because it actually at this point of time we were like desperate because we couldn't exploit the format string vulnerabilities for multiple reasons. We had no clue why. So the normal procedures just didn't work and we had no clue why. So we used strace and called status, the TS status binary, fed it some user supplied input. So, and this is what basically happened. So the user calls TS status binds to a random TCP port on all interfaces. Okay, so the user starts the binary, then the binary chooses some random port, it opens up this port, then TS status sends the port number and the supplied user input using a local message queue. So user input goes into the message queue, port is open. Then the file system grabs some stuff out of the message queue, as we found out later, connects to this port, to the supplied TCP port, and sends the parsed interpreted results back to the TS status binary. And then TS status basically prints everything. So, okay, looking at a glance, looking at strace, nice architecture, looks quite interesting. Okay, but why does the file system daemon crash? So if you look at what is sent over the socket, so this is basically the stuff from strace you see right here. So you see a read. So we see that we are receiving some stuff. And then there are two things that should come to your attention when seeing this. The first thing is the last line just shows us the message that is displayed. So this is something that TS status writes out to the shell. The previous error was detected, or the file system blah, blah, blah is not shown, whatever. And the second thing is that this is the string that we are printing out should be actually in the socket communication. And some parts of it are in the socket communication, but if you closely read and look, you see that the socket, over the socket from the file system daemon, we see that there is a format string send. I see many question marks. That's actually how we looked at as we have seen it, because we would have expected that there was just the string, and this string is received over the network and it is printed out. But in this case, the file system daemon is not just sending the result back to the binary, it is sending a format string to the binary and the corresponding stack for it. Nice. Because now we found out why actually the file system daemon is crashing. So here at point 4, the file system daemon is connecting back to us and it's sending the result back. The result is a format string plus the corresponding stack. And if you send a %s, the stack creation on the file system daemon side fails and it just simply crashes. So this is the denial of service scenario that we investigated. Okay, so now with this knowledge, we now know that we actually, as the attacker, may be able to pass our input and our stack to the binary. So we could send our own format string with a completely controlled stack over the network, and therefore code execution should be possible because we have full control of the stack that we're sending and we're in full control of the format string vulnerability. But there are two challenges. One challenge is, as I said, it's a random port that will be open. So how do you get to that port to do something, to speak to the binary? And speed is an issue too, because once you know which kind of port to connect to, you need to make sure that you are the first one and not the file system daemon. So you need to be fast in doing this. So for the first point, or the random port problem, we did some IDA and did some reverse engineering and did some strings over the binary, and we found out that there is an environment variable which states GPFS command port range. And this is basically an environment variable that tells TS status to use this port instead of a random port. Okay, fine. Now we solved the problem of having the random port. Perfect. And now we have this race condition right here. The problem is that in our initial setup with the virtual machines that we had running, we had the problem that we did not win the race. We even came up with some obscure C code that tried to win the race against the file system daemon, and it didn't work out. And I don't know if Frank's here, but if he's here, thank you, Frank, because he said, like, you're dumb, just takes 2 CPUs for the VM, and that should do it. And actually, we did that, and then we were fast enough to win the race. So, and even, like, I think that even Java would have did it to win the race, so we were quite fast by that time. So winning the race condition is no problem anymore. So now, at this point, we know the port to connect to. We can win the race to dump anything into the binary that we want, our custom stack and the format string. And the other thing that we need to care about is there some kind of authentication? So can we just talk to it and that's it? Looking at the binary, we found out that there's some sort of cookie value that is checked before doing anything. And it turns out that this is actually the process ID of TS status. So if you're running TS status, then you would have to tell it the process ID. And if this process ID is the same, then TS status would let you in, to say so. Okay, so what you do by exploiting this is the first part would be set the environment variable, win the race, send the PID of TS status, and the second part, get code execution because you control the stack, you have the format string vulnerability, it should be easy. So the problem with doing this, or we encountered some additional problems and some additional stuff that helped us out. For example, the binary is not Pi enabled, which means it had constant addresses, which is quite good. The system libraries were randomized, which is bad, and what you normally would do when you have a format string vulnerability, you would just use an info leak. So remember that %x gives you values from the stack. And if you are, there might be a chance that dumping multiple values from the stack will give you a pointer to somewhere, and from this pointer you can calculate your offsets and then write to the address that you need to, right? So an info leak actually was not possible in this case because it was our stack. So the stack that we control the stack, and we're sending the stack over the network basically. So there is no point in dumping stack out of the binary with the %x because this is not working because it's our stack. So info leak is not possible, which makes things a little bit harder. We went on to overwriting global offset tables that worked out pretty well. We had some problems there too, actually. This was actually the point where Enno was like, okay, so how far are you? How good is the exploit? Is it working? Is it reliable? And actually we were like, yeah, well, it's not that straightforward and we might need a little time, but everything will be fine. Yeah, so what you do when overwriting the global offset table is normally that you need to find a library function that is called after the format string is triggered. So what you do is the format string is triggered. With this format string, you override the global offset table and override a function pointer, which will then point to your ROP chain that you would have to use in this case. The problem was that we had a very small binary, and there was no usable stack pivot available at this time. So we came up with the idea, okay, so just override the library function with a different function. So don't let it point to the ROP chain, but let it point to, for example, system or some kind of exec call. Turns out there even is an exec call in the binary, but the problem is that it was not compatible because we were using fprintf all the time, and system or exec that we could have used once a string, and fprintf, the first parameter to fprintf is actually a pointer to a file, I guess, and this will not work out, right? So we could not achieve code execution with this. So everything gets harder and harder and harder. But never give up. There's an alternative approach that we found out. We were looking at the message types that you can send. Actually, these are the message types that the MFSD will be sending. So you could have a message type like display a message, give a general error, and then we found out that there is a message type which is called edit message. Okay, so what does this do? So basically, what it does is the server sends the edit message to the TS status binary with arbitrary text content. Then there is an environment variable which is called editor. If this is not there, it defaults to VI. And what happens is that a command line tool writes the content to a temporary file, drops the privileges, which you can see right here, and then opens the editor specified in the environment variable. So we have some sort of injection point into an exec call right here. So the user, in the normal case, can edit the file. So it's like really you're sending this, you're calling TS status, then VI pops up, you can edit the message, save it, close the editor, and the data is sent back to the server. So what we did now is we used this or a kind of injection to say so into this exec call combined with our format string attack. So we sent 3 messages. The first 2 messages trigger the format string vulnerability. One is overwriting set group ID, one is overwriting set UID with the address of a ret, which basically renders the set UIDs down here as a knob. So we are overwriting set group ID and set UID with a return address, so nothing happens right there. And then in the third message, we trigger the edit message function, and as an editor, we specify Perl. And the content that we control is something like this. So this is basically our shellcode that we are passing to Perl. TS status actually thinks, yeah, well, this is an editor, let's open it up. It's called Perl, let's open it, and let's pass it this code. And then basically Perl does its dirty job. So we have a demo. Demos are always on your right. So what you see right here is the demo page. What you see here is the slides. So
yeah,
Felix.
so the Python script on the left shell is basically the script trying to win the race condition. So we just can start the script, which will just loop until something happens. And then we have this nice invocation of the ZUID binary using these 2 environment variables. And we can see a lot of our format string dumped to the output. And now you should see a root shell. So if I enter IDs, you can see we are root.
Yeah. Yeah, so that worked out perfectly. So, yeah, we actually resubmitted this bug. And now the CVSS is increased a little bit from 4 to 6.9. And yeah, they actually acknowledged that it is exploitable. So remember this structure. We are at the user space utilities chapter. We have a local privilege escalation now. We are a format string, whatever, hybrid injection exploit. And so we have solved our first challenge. And for the next part, Felix is going to add on.
Okay, so we spent too much time working on some kind of format string vulnerability, so I was kind of motivated, or we were kind of motivated to look into other parts of the system as well. So the problem with the current exploit basically is we have a local privilege escalation on one system, but we might also want to compromise other nodes in the cluster. So we might be lucky and find another vulnerability that allows us escalation from one node in the cluster to different nodes of cluster. Well, it seems to be the case, if you look at the documentation, that a prerequisite of IBM GPFS is actually that you are able to SSH from one node in the cluster to all other nodes in the cluster with the root user ID without a password. So if you own one node, you own all of them. And so we don't even need some kind of exploit or Perl script or something like this. They have built-in functionality for this. So there is the mmdsh command, which is the distributed shell, basically. And you give it a list of nodes and a comment, and then you can see you execute comment on all of these nodes with root privilege. Of course, this is only possible if you are root on a single node. So we still have an open question: what happens if you are completely from the outside? So you don't have a local account on any systems inside the cluster. You only have an IP address of one of the cluster nodes. Well, we already talked about this MMFSD, the file system daemon of GPFS. It's the main network daemon or the only network daemon used by this file system, and it listens on TCP port 1191. And the interesting thing is, it's listening on every interface by default. So you can imagine if you have a supercomputer with like dozens of network interfaces, probably only a couple of these are actually used for GPFS communication. But by default, GPFS is happy to listen on all of these interfaces. So of course, this is an interesting attack surface. Now the GPFS daemon is mainly used for cluster communication, so for communication between nodes in the cluster and for the synchronization of the state. And also for network shared disks. So if you have a disk that is only attached to a single node in the cluster, all file access will be communicated using this daemon. It works by opening multiple persistent TCP connections, so these TCP connections will stay alive for the whole lifetime of the cluster in an ideal case. And then the nodes are mainly exchanging heartbeat messages, so we are still alive, and file synchronization for these network shared disks. And what's interesting, if you actually look at this traffic on the wire, so if you are in a man-in-the-middle position or something like that, you can see that the cluster communication by default isn't encrypted in any way. So this is actually a file I wrote where I wrote hello troopers, and this is going over the network like this. So this is something you have to keep in mind. Of course, in a man in the middle position, we now would be able to like manipulate this message context arbitrary. However, it might be the case that we are in a cluster system where there isn't any sensitive data stored on this network shared disks, or the communication between the cluster nodes might be actually occur on a private interface which we don't actually see. So this is probably the more realistic attack vector. So it would be really nice to have something like a remote exploit against the file system daemon. So we did some kind of protocol analysis to understand how this communication actually occurs. And it's a stateful protocol, so you have like a persistent connection between cluster nodes, which starts with a hello packet, and afterwards they exchange simply data packets like this one you've seen in the slide before. SSL is possible, but as we said before, not enabled by default for performance reason, and because until recently they didn't support activating it without rebooting or without restarting the cluster. So we can't simply replay something we captured to like trigger a file write. Instead, we have to send a valid hello packet so we can create a valid connection. Now, if you look at a hello packet, you see a couple of interesting looking fields. If you are familiar with IP, so this is only the TCP payload dump. This is important. This doesn't include any lower layer protocols. So what we can see in this message format is like a magic constant, and we see the IP addresses of the source and the destination node stored inside the TCP payload. So this looks kind of strange. In addition, we have timestamps, a cluster ID that uniquely identifies a certain cluster, and then you have TLV values, so type length values for certain operations. Now, we were wondering what is the actual authentication for this hello packet. And as it turns out, the idea of MMFSD is that only nodes that are part of the cluster should be able to build up a communication. The problem is this check, if you are part of the cluster, is based on the IP address of the sender you embed into the TCP payload. So of course, you can simply spoof a valid node address. So you put like a valid node address inside your TCP payload, and then we can communicate as part of the cluster. Of course, this opens like an extremely large attack surface by design, because now we can like write arbitrary file stuff on network shared disks. Still, we want to have remote code execution, so a shell should pop up. And if you open this daemon in IDA, you can find all the different message handlers for these different type of messages. And one we found like instantly was the handle cc message mm remote message. So they are so nice and include debug symbols in their binary so you can see the actual message name. And what this does, this message type, it basically takes your message payload and passes it as argument to one of 3 local command line tools that are available on the system. And as we have seen, this feature is really old, so this isn't actually used anymore in current GPFS versions. And we can see this because remote is actually the only binary that's still existent. So you can try to trigger execution of a binary that isn't even included anymore in the actual distribution. So remote is a bash script, which is always cool. If you have a bash script, you can execute it with root privilege from remote. And it has like a couple of thousand lines of code, and it's surprisingly good. So if you are interested in writing well-quality bash scripting, this is a prime example. However, by design, it's already very powerful. So it has like built-in functionality to unmount and mount arbitrary disks and stuff like this. So still, we wanted to have something even simpler, so like a command injection. And if you call it like this, and it's important, we are able to call this over the network, so remotely, without any authentication, it will create the file Pr0ken. Yeah, of course, we also have a demo for the remote command execution. So, I have to set up. So the problem is for this command injection, you can't simply do this with one command injection because certain kind of special characters aren't allowed. So you can't simply put a Perl script inside your command injection. Instead, we are doing it by using a first command execution to download our Perl backdoor from a web server, and then the second command injection will actually trigger the script. We have some kind of timing issues, so this actually has to hit. So I might need to execute this exploit like twice or 3 times. Yeah, but this was like on the second try, and you can now see I got a communication from the GPFS node, and if I enter ID, I'm root. So this is completely remote root. Now, the interesting part about this bug was that they weren't really able to patch it. So at least they learned their lesson and we got the right CVSS score, at least for now. But the problem is, of course, this is a design flaw of the protocol, and they actually have a reason for why they are looking at the IP address stored inside the TCP payload, because you have to imagine you might have something like failover. So if one network interface dies, you still want to be able to communicate via the cluster, so you can't simply use the source IP address. The only way how you can fix this is by enabling SSL, because this supports authentication over SSL certificates, basically client certificates you store on the file system. So they have now released a patch on Sunday that allows you to enable SSL during normal operation of this cluster. So because this seems to be a really big problem for many of their customers, that they have to be able to enable this during normal operation. So this is kind of an impressive technique or a patch release. So if you use GPFS, please enable SSL right now. Now, we still have something left. We already got local root and we got remote root using the communication daemon. And then we have something, so we have this kernel module. And now we show, so this kernel module creates basically a device, a Linux device, and this is used for the communication between the GPF user space tools and the kernel itself. And it uses normal IOCTL calls for this. Now, the problem is that the GPFS core libraries need to talk to this device, so libraries you would not use in your normal user space application. So they can't simply do the permissions for root only. Instead, they have to allow normal users to use this. So they need to add a check to every single IOCTL call, and there are like 150 IOCTL calls in this binary. So we looked at the core and looked at a couple of IOCTL handlers to find a vulnerability. If you want to look at these, you have these three modules. Again, MMFS26 is like the only one that actually performs work, and it's binary only. But if you start looking at these handler functions, you see a nice handler function kernel wait for flock, file lock probably, which is the IOCTL call number 39. And it doesn't have any privilege checks. So you can use this unprivileged from the local system. And it's called with user-controlled arguments. So the variables arg are actually coming from user space. And if you have ever written C, you see something like this. This is an arbitrary write in kernel context. So we control arg4 and we control arg1. So it's like game over. So we reported this to IBM, but didn't provide a full privilege escalation proof of concept at this time. But our mail clearly stated this is like trivial privilege escalation on a normal Linux system. Well, they released a patch on Sunday, but they didn't agree because clearly an arbitrary write is only a denial of service. So, yeah, I don't want to spoil it, but of course it's not a denial of service. It's actually quite trivial to exploit. We use this arbitrary write to write an address of our own ring0 shellcode into one of the unused entries of the IOCTL handler table. Then we call this back.ioctl using our user space binary, and the kernel executes the shellcode and changes the privileges of our current process to root. And of course, we have a demo for that. We're quite fast, so I have to...
Are we quite fast, Michael? How much time? 15 minutes.
Okay, so that's fine.
Yeah.
So we have this nice little exploit. I have to compile it. And if I execute it, you can see it even has a logger, and it's again root.
Yeah, we should state that we even had time for the logo, right?
Yeah. So. I think the logo took more time than the exploit did. Okay, so remember the structure of our talk. We looked at the user space utilities, they were broken. We have a remote root exploit against the communication daemon, and just for fun, we also got root on the kernel, or against the kernel module. Now the only thing that was left to do was to actually talk to IBM about all this stuff. So IBM's response was extremely professional. So they still have like these optimistic estimation of exploitability, as I call it. So if you don't provide them with a with a code execution exploit, they probably assign a denial of service CVE score for it. But other than that, they're really impressive. So they release patched for all these 3 bugs on Sunday, so just in time, which means they only took like 30 days from our official report to the actual patch release. As we said before, the patch for the remote bug is basically enable SSL. So countermeasures for all these attacks are you have to apply the vendor patches, still enable SSL to mitigate the remote issue. And of course, as you have seen, GPFS is only usable if all nodes are fully trusted. So if one single node is compromised, all the nodes in your cluster will be compromised as well, because like this distributed SH comment I've shown you is created by design. And we strongly recommend to firewall non-GPFS interfaces, so interface when no GPFS communication occurs on port 1191, so an attacker can't simply speak to this daemon from the outside.
But maybe we have to tell them that we did some investigations on the internet.
Yeah, so we did perform a scan for 1191, and there are some systems available, let's say it that way.
Yeah.
Okay, so I think, yeah, lessons learned. Of course, the attack surface is key. In this case, the attack surface of GPFS is like incredibly large on all layers. So we have a lot of ZUID user space binaries, we have an extremely complex kernel interface, and this daemon is also it's really impressive in the way what it does, so the distributed file system actually works, but of course it's like a perfect playground for memory corruption vulnerabilities and stuff like this. This is like complexity kills. And of course, if you are auditing binaries that were originally written in 1993 and support like different kind of Unix operating systems as well as Windows, you will have problems in this. And if we look back to our old user space problem we had at the beginning to exploit this TS status binary, never give up, try to exploit it, and then look at other stuff in the same system, you might still find some interesting bugs. And it's always good if you're having somebody to pressure you into talking at the conference.
Yeah, but don't tell Enno.
Yeah, don't tell Enno about that, but because then you actually have to do the real work. So that's it from our side. Thanks for your attention, and we're happy to answer your questions.
Okay, questions?
Thanks, guys. You took a look at the TS status set UID binary. Did you look at many of the other binaries, set UID binaries that were listed?
Because the problem is that TS status is basically, or many of the binaries are just symlinked to each other, as I mentioned shortly. So we did not took a look at, TS status was enough in this case, so we didn't took a look at the other ones because most of them are symlinked to each other, and depending on what name the binary has in this case, a different code path will be executed. So most of them are just one big binary, and depending on what name it has, it just executes different code paths.
And you can see they actually compile. So this is basically they have this communication stuff that supports the edit message and stuff like this. And this is the same for all of these user space binaries, which is just statically compiled in, because the TS status binary never uses the edit message functionality, but like the library supports it and it's compiled in, so you have this attack surface.
Another question, if it's okay. On your remote exploit, is the communication to the NSDs, is that required to come from a privileged port? I.e., is your MM status?
No.
No, okay.
No.
Awesome.
They're only, so for the, you mean the exploitation of TS status? So if you connect to this?
Yes.
They are only check, so the original cookie or the authentication was only that you send the process ID of TS status via TCP, which is kind of trivial if you are on the local system. Now they added some kind of random cookie, which should be more secure, but to be honest, we didn't look at that. No. So it might still have some problems.
Thank you.
Okay, more questions?
Sergey.
Yeah.
Sergey.
So when I saw that they were sending the stack, right, I thought, well, serialization, RPC, but did you get the idea? What possessed them to design a system like this?
Yeah, it was 1993, and they had like a few days off. I don't know.
We actually talked to one of the developers, and he was very competent. And I think they see the problems, but it's like a growing architecture, and they are trying really hard to stay backwards compatible. So probably somebody wrote it like this in 1994, and they are still trying to keep this up and running.
So while you were reversing that, right, did you see the traces of any particular tools, like their RPC tools? I mean, they invented RPC, didn't they? Right?
For me, it looks completely handwritten, so it's not like some kind of automation or something like this.
Thank you.
Okay, more questions.
Just out of curiosity, what systems were you hitting that were running GPFS? Were they supercomputers or were they just general clusters? Or can you not answer that
question?
Next question.
Yeah.
Cool.
Okay, I hope you have a death hand system in place. Okay, last chance to ask questions. Otherwise, we will do an early lunch break, and you can talk to Florian and Felix in person if you like. Okay, Sergey?
Yeah, maybe just a hint and then a follow-up question. I have the pleasure to running the backup software from IBM, and it's called TSM Tivoli. So just a hint, if you're kind of bored.
We will note it down. Yeah.
And a general question, not about the exploits, but do they still put the configs into the bin folder, like they do in other software I saw?
It has kind of an interesting layout on the file system, let's put it that way.
Okay, thanks.
Okay, so Florian, Felix, thank you very much. Great work.